Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying definite integrals lecture 3. In this lecture we'll be talking about property 7, that is periodic property, limit of a sum and Leibniz theorem, right? So let's begin our lecture with the property 7, that is periodic property, and it is applicable only for periodic functions, right? So it has three subparts 1, 2 and 3, and all of them are more or less similar. It's not like they're very different, they are more or less similar, right? So the first property is integral 0 to nt, where t is the period of this function. Integral 0 to n t fx dx equals to n times integral 0 to t fx dx. So let's try to understand that with the help of a graph. Let's say we have a function fx equals to modulus of sine x. Okay. So the graph would look like this, right? So this is pi, this is 2 pi, this is 3 pi, and this is 4 pi. I'm sure you all know how to plot modulus of sine x. Okay. So the period of this function would be pi, right? Basically, the function is repeating itself after period of pi. Okay. Now we can say that if this area is a, area under the curve from 0 to pi for this function is a, then this should be a, this should be a, this should be a. Agreed, because this is a periodic function where the function is repeating itself after period of pi. Okay. Now, if you want to calculate integral 0 to 4 pi modulus of sine x dx, can we say that this is same as integral 0 to pi 4 times modulus of sine x dx? Why? Because this area, this area, this area, and this area is same. We want to calculate integral, basically area from 0 to 4 pi over here. So what we can do, we can just calculate area for one single cycle. Rather than calculating for 4 cycles, we are just calculating for one single cycle and multiply that by 4, right? We can do that. So that is what property 1 is all about. Okay. So over here it is written integral 0 to nt, where n is the number of cycles, t is the period, fx dx equals to n times, that is number of cycles, multiplied by integral 0 to t fx dx. Simple. Now let's talk about property 2. So let's take the same function once again. We have fx equals to modulus of sine x, right? So the graph would look like this. This is pi, this is 2 pi, this is 3 pi, this is 4 pi, period is pi over here, right? So the property 2 says if we are going from a to a plus nt, basically integral a to a plus nt fx dx equals to n times integral 0 to t fx dx. Okay, so what does that mean? Let's try to understand that with the help of graph. Okay, so let's say a equals to pi by 4 over here and a plus nt, that is pi by 4 plus n, let's say 3 into t is pi, right? T is nothing but period of this function. So a plus nt equals to pi by 4 plus 3 into pi, right? So basically we are going from pi by 4 to pi, 2 pi, 3 pi, that is 3 pi plus pi by 4 till here. Okay, so we are going from a equals to pi by 4 to a plus nt, that is pi by 4 plus 3 into pi by 4, right? So what is happening over here? We want to calculate this area, this area, this area, and this area. We are missing out this particular area. Now, since this is a periodic function, can we say that integral 0 to pi by 4 mod sin x dx is same as integral 3 pi to 3 pi plus pi by 4 modulus of sin x dx, right? This area, this particular area is same as this particular area, right? This particular piece, right? We want to calculate this portion, this portion, this portion, and this portion. So can we shift this over here, right? So that would make this cycle as complete. This one will become complete, this one is already complete, and this one is already complete, right? So we have got 3 cycles over here. So initially what we were doing, we were calculating area from pi by 4 to 3 pi plus pi by 4. But right now what we can do, we can calculate area for these 3 cycles, because virtually we have shifted this particular piece from here to here. So that gives us area of 3 cycles. And we know how to calculate area of 3 cycles, that is 3 multiplied by integral 0 to pi modulus of sin x dx. This is what we are doing over here in this property, right? So over here n is the number of cycles, ultimately n is the number of cycles. So that's what we have done over here, n times integral 0 to t. Simple. Agreed. Over here n was 3, so that's why we have got 3 times integral 0 to pi modulus of sin x dx. Simple. Now let's talk about property number 3. So property 3 says integral mt to nt fx dx equals to n minus m integral 0 to t fx dx. M and n belongs to integer, right? So let's try to understand that with the help of an example. Let's take the same function once again, modulus of sin x. Okay, so we have the graph as like this, right? So this is pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and 7 pi, right? Let's say m equals to 2 and n equals to, let's say, 7, or let's say 6. Okay, now we want to calculate from here to here, from here to here. We want to calculate the area under the curve from 2 pi to 6 pi. We want to calculate integral 2 pi to 6 pi modulus of sin x dx. Okay, so according to property, it says that it becomes 4 times, basically 6 minus 2 times integral 0 to pi modulus of sin x dx. Okay, so again we are doing the same thing. We are just calculating the number of cycles. 1, 2, 3, and 4. We have 4 cycles. So 6 minus 2 becomes 4 cycles, right? So that's why it becomes 4 times integral 0 to pi modulus of sin x dx. Simple. All we have to do is calculate the absolute number of cycles, right? That's what we want to do in case of periodic property, and that would solve most of our problems. Okay, and now let's solve this example. We have integral minus 1 to 2 e raised power fractional 3x dx. Now we know that fractional x is a periodic function with period 1. Fractional 3x is also a periodic function with period 1 by 3. And a composite function created out of fraction 3x, that is e raised power fractional 3x, is also a periodic function with period 1 by 3. Right? And now since we know that e raised power fractional 3x has a period of 1 by 3, we can write this integral as integral minus 3 times 1 by 3, right? To 6 into 1 by 3 e raised power fractional 3x dx, right? Now we can see that we have total of 9 cycles. From minus 3 to 6, we have total of 9 cycles. Okay, so we are using this third property, mt to nt. So n minus m. Over here, we have n equals to 6, m equals to minus 3. So overall, we have 9 cycles. 6 minus minus 3, that is 9, right? So that becomes 9 times integral 0 to 1 by 3 e raised power fractional 3x dx. Now for 0 to 1 by 3, this fractional 3x would be 3x only, right? Because that would be just one cycle. Now you can simply integrate this one, right? And now let's talk about this question. We have integral 0 to 2000 pi dx upon 1 plus e raised power sin x. Okay. Now we know that sin x is a periodic function with period 2 pi, right? So we can say that 1 plus e raised power sin x, that is a composite function created out of sin x, that is a periodic function, is also having a period of 2 pi, right? So we can say that this integral can be written as 0 to 1000 into 2 pi dx upon 1 plus e raised power sin x, right? Now this becomes 1000 times 0 to 2 pi dx upon 1 plus e raised power sin x. Now this becomes a very standard integral, right? Now you have to use the property of f of a plus b minus x, right? So I'll keep this as homework because that we have done a lot. Okay, and now let's talk about Leibniz rule. So if the function is continuous, that is the most important keyword over here. If the function is continuous, then only d by dx of integral gx to hx ft equals to f of hx dot h dash x minus f of gx dot g dash x. That's a very simple formula you have to remember, and we won't be deriving this formula. I just have to remember this formula. Okay, but the most important thing over here is the function should be continuous. Fx should be continuous. That is the most important point, right? And now let's solve this example. If fx equals to integral e raised power 2x to e raised power 3x t dt divided by ln t, where x is positive, find the derivative of fx with respect to ln x when x equals to ln 2. Okay. Now we can see that they have asked multiple concepts. So the first one is Leibniz theorem. Second one is differentiation of one function with respect to other function. Okay. Now they have asked d fx divided by d ln x, right? Now based on understanding of methods of differentiation, this can be written as d fx divided by dx, basically f dash x divided by d ln x divided by dx. That is derivative of ln x with respect to x. Okay. So this is nothing but f dash x. So before calculating f dash x with the help of Leibniz theorem, we should understand that the basic most rule of Leibniz theorem is this function should be continuous, right? This function should be continuous. Only in that case we can apply Leibniz theorem. Okay. Now we can see that t is continuous, ln t is also continuous. So can we say that t by ln t is also continuous? Yes, in most of the cases. In most of the cases, if this is continuous, then their division is also continuous. But this should not be zero, right? For all the points we're considering, this should not be zero. In that case, we can say this by this would be continuous. Okay. Now ln t can become zero at t equals to 1, right? Now I can see that x is positive over here. For x equals to 0, these limits would have been 1 and 1 only, right? For x equals to 0, because that would be e raised power 0 and e raised power 0. But since x is positive, we can say that these limits would be something 1 plus and something 1 plus, right? Basically, any positive value which is bigger than 1, right? So if we are talking about bigger than 1, in that case, this won't become 0, right? So that's why this function is continuous. Now that we have proved this function is continuous, we can apply Leibniz theorem. Okay. So that would give us f dash x as e raised power 3x divided by ln of e raised power 3x multiplied by derivative of this one. That would be e raised power 3x multiplied by 3 minus e raised power 2x divided by ln of e raised power 2x multiplied by e raised power 2x multiplied by 2, basically the derivative of this one. Okay. Now, can we write this as 3x only? Why? Because ln of e raised power 3x, that would be 3x multiplied by ln of e, and that is 1. So this can be written as 3x and this can be written as 2x. So ultimately what we have got, this gets cancelled out. So we have got e raised power 6x by x minus e raised power 4x by x. So basically e raised power 4x e raised power 2x minus 1 divided by x. So this is our f dash x. Our question is not over because this was just one part. We have to also calculate d ln x by dx, basically derivative of ln x with respect to x. And we know that d ln x divided by dx is nothing but 1 by x. Okay. So if we find out dfx by dx divided by d ln x divided by dx, that would be e raised power 4x e raised power 2x minus 1 divided by x whole divided by 1 by x. So this gets cancelled out. So what we have got, e raised power 4x, e raised power 2x minus 1. This is our answer. Okay. Now we have to apply x equals to ln2 over here. You can apply that over here and you'll get the answer. Okay. And now let's talk about the concept limit of a sum, which is nothing but converting limit of a summation series into integrals. And for that, we'll have to go back to our understanding of integrals with the help of area under the curve. Okay. So let's say we have this curve over here. That is fx. And we have to find out area under the curve from point A to point B. How do we do that? We do that by converting this area or dividing this area into rectangles of equal width. Let's say the width is h and let's say the number of rectangles are n. So n equals to number of rectangles, h is the width. Okay. Now this is our rectangle 1, this is 2, this is 3 and this is the nth rectangle. So for first rectangle, this point is nothing but f of a, and that is same as the height of this rectangle, right? For this particular point, this would be f of a plus h, and that would be the height of this rectangle, right? Because this point is nothing but a plus h. So this point would be f of a plus h, and that is height of this rectangle. So for first rectangle, height is f of a. For second rectangle, height is f of a plus h. For third rectangle, height would be f of a plus 2h. So for nth rectangle, height would be f of a plus n minus 1 h. Agreed, right? So how do we find out the entire area? So we have to add all these areas. So for first rectangle, area, that is delta 1, would be f of a multiplied by h, right? Similarly, delta 2 for second area, that would be f of a plus h into h, right? Similarly, delta n, that would be f of a plus n minus 1 h into h. Agreed. So if we want to find out the entire area delta, that would be h times fa plus f of a plus h plus f of a plus 2h till f of a plus n minus 1 h. Agreed, right? Now we can see that this length is b minus a. This coordinate is b, this coordinate is a. So that's why this entire length from here to here, that is b minus a, right? And we have n rectangles of equal width. Okay. So can we say n into h would be b minus a, right? B minus is the total length, n is the number of rectangles, h is the width of one rectangle. So n into h is b minus a. So can we say that h equals to b minus a upon n? Agreed. Now we have to use this over here. So delta comes out as b minus a upon n multiplied by f of a plus f of a plus h plus f of a plus 2h till f of a plus n minus 1 h. Okay. So this is what has been written over here. Now to approximate the area of this entire curve from points A to B, what is happening? We are missing out this point, this point, this point, and this point, right? So for that we have to apply limit n equals to infinity, n approaches infinity, such that this becomes negligible, right? So if you apply limit n approaches infinity, so these all gaps are becoming negligible. So that's why we are able to estimate the area under the curve, right? So this becomes delta equals to limit n approaches infinity b minus a upon n and this one, right? Understood till here? Okay. And now let's talk about a special case where a equals to 0 and b equals to 1. Okay. In this case, h equals to b minus a upon n. That becomes 1 upon n. So h becomes 1 by n for this special case. Okay. So this becomes 1 multiplied by limit n approaches infinity 1 upon n f of 0 plus f of 0 plus h. H is nothing but 1 upon n till f of 0 plus n minus 1 into 1 by n. Agreed. Now this can be written as limit n approaches infinity 1 upon n f of 0 plus 0 by n plus f of 0 plus 1 by n till f of 0 plus n minus 1 by n. Right. Now we can see that this is variable over here 0, 1, 2, 3 till n minus 1. Right. So this can be written as limit n approaches infinity 1 upon n sigma r equals to 0 to r equals to n minus 1, right? And this becomes function of r by n, right? Because r by n are going from 0 to n by n. So this summation series has become like this. Okay. But there is one problem over here. What we have done is we have taken a special case of a equals to 0 and b equals to 1 and found out this expression. But can we generalize this expression? Because there can be a case where a equals to 0 and b equals to 3, let's say. Okay. So let's try to understand that. Let's say a equals to 0 and b equals to 3. Okay. In that case, b minus a would be 3. Right. We skipped that part because over here b minus a was 1. But over here b minus a equals to 3. Okay. Now in this case, if we go back to the basics, we divided our entire region into n rectangles. In this case, we'll divide that into 3n rectangles. Okay. Such that h is still b minus a upon 3n. That is 3 upon 3n. That is 1 upon n. Basically, this thing is still 1 by n only. Right. This becomes 3. This becomes 3n. So it still remains 1 by n only, right? So that's why our expression stays the same. Only thing that changes over here is the limit, is this limit. So we'll go from r equals to 0 to r equals to 2n minus 1 or 3n minus 1 or 4n minus 1, whatever. But everything would stay the same, right? So that's why we can generalize this expression and we can make a comparison with the integral. Okay. So how can we do that? So what we are doing over here, we are comparing 1 by n as dx. So 1 by n as dx. We are comparing r by n as x. R by n as x. Okay. And what we are doing, we are comparing this sigma with these limits as integral a to b. Okay. So sigma r equals to 0 to n minus 1 is integral a to b. Over here it's 0 to 1. So basically n minus 1 is being compared with n minus 1 upon n, limit n approaches infinity, n minus 1 upon n, and 0 is compared with limit n approaches infinity, 0 upon n. Okay, so you have to make all these comparisons to convert summation into integral. Okay, and now let's solve this example. Find the value of limit n approaches infinity, 1 upon n plus 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon 4n. Okay. Now in this case, the first step is to take 1 upon n is common, because ultimately we are going to have dx in the integral. So that's why we have to take 1 upon n is common first. So this becomes 1 upon 1 plus 0 by n, right? Plus 1 upon 1 plus 1 by n plus 1 upon 1 plus 2 by n till 1 upon n plus 3n by n. Why 3n? Because this can be written as n plus 3n, right? So this becomes 1 upon n plus 3n by n, right? Now limit n approaches infinity. This becomes 1 upon n sigma 1 upon 1 plus r by n. Basically, this is the variable over here. R going from 0 to 3n. So r equals to 0 to 3n, right? This is our general expression which we have to convert into integral. Now this can be written as integral, right? We have dx over here, this portion. We have limits from 0 to 3n by n, that is 3, right? And this becomes 1 upon 1 plus, this can be replaced by x. So this is our integral which we have to find. So this summation is nothing but this integral, which is very simple, right? So this is how you have to solve these questions. Okay. So today's lecture was still here only, and this was the last lecture of definite integration. And with this, we are done with the definite integration. So from the next lecture, we'll be talking about area under the curve. So let's meet in the next lecture. Thanks for watching.